Okay, so I will continue from the last time, the geometric decomposition to elementary orbifold. So first of all, there is a decomposition to elementary orbifold because whenever you do this, you decrease the absolute value of the eigenvalue whenever you cut up some element orbifold. So in the end, you will always get left with elementary orbifold, so you cannot do anything anymore, right? Uh, so, uh, uh, so you get in the end, you can also do this with geodesics or the simple core geodesic or mixed type geodesic orbifold, so that sigma is just some elementary decomposition to elementary to orbifold, or so something with some boundary one over per Silbert, maybe additionally. So that's the all we're going to get, right? Because you cannot do anything further anymore, right? So the Thurston theorem is that the sigma is compact over with empty or boundary or with negative order characteristic different to elementary to overboard and uh, um, Ah, so this may not be empty, so it could be non-empty, right? Sorry. So then the deformation space of a hyperbolic RP2 structure. So this is not necessary. You don't need this RP2. Just need the uh, uh, you can drop this, so you don't need that. So structures on sigma is homomorphic to three times Euler characteristic underlying space X sigma, and then the 2k plus L plus 2n, where k is the number of cones and L is the number of corner reflectors, and n is the number of boundary for orbifold. So this may have a geodesic cross curve boundary or some geodesic boundary for orbifold. Okay, so these that can happen. Okay, so those are the Thurston theorem, and so the proof is that for any elementary 2 before S, TS is just homeomorphic to T boundary S. So boundary S is just going to be the some geodesic boundary components or the boundary for orbifolds. Okay, and so these will be just the product of. So in this case, of course, you need to de-silver everything to do this, right? So a product of R plus for each component of boundary S corresponding to the hyperbolic metric length of boundary S. Okay, so that's the first thing. So then we'll have to do the gluing construction to get the final result. Okay, so actually, so this theorem is actually independent of the whether you use silver some boundary components or not. It doesn't matter, right? So because this doesn't change, but this may decrease, but you will get increasing here in L, and then so on. So that's the basic. It doesn't matter whether you silver the boundary for orbifold or not. Okay? So then for the uh, right to understand this, we need the generalized hyperbolic triangle theorem. Okay, so the okay, so you can look at hexagon. So you label hexagon with the I mean the perpendicular angles in the hyperbolic plane. And so it will be labeled A, beta, C, alpha, B, gamma. So alpha is opposite A, and then beta is opposite B, C is gamma is opposite gamma. Okay, so this is six sides of the hexagon labeled like this. And then the pentagon again, you have five geodesic sides. So A, B, which meets an angle, right angle, and the in angle gamma, and then the alpha, C, beta, gamma, beta, and then there's gamma. Okay, So if you see the picture, so it'll be like this. So this first one is A alpha and then B, A, B, C and beta opposite. And here A, B, but the gamma now, you look at this gamma is shrink to an angle. Okay, so this is a really, if you see it in projective space, it makes sense because it's sort of like a hyper ideal and now becoming an end and then ideal point and then it becomes elliptic. So then this kind of makes sense here. And then C is C, and then so beta is opposite A, and then A is opposite beta. And the next one is this square, I mean quadrilateral with the alpha beta here, and C is the angle, and then gamma here, then BC. So here actually you can think of this alpha and beta, alpha beta becoming an angle. Okay, so it becomes an ideal point and then becoming an angle. And then finally, so alpha beta gamma all becoming an angle like this. Okay, so those are the four generalized hyperbolic triangles. So this is actually a triangle because you can extend this and then it will meet outside the hyperbolic space. At least in the Klein model or Poincare model, it will meet outside the where I should say more like yeah, more precisely in the Klein model, it will look much better, right? So these will actually meet. And then gamma is kind of dual to that point in the projective space. So in the projective space, these make much sense. How you can deform gamma to gamma here and then so on. So the next one is a quadrilateral disk bounded by four geodesic sides A, B, C, gamma, and then AC median angle beta and CD median angle beta. And the two remain ones are right angles, and then triangle is just the ones we already show. So these are sort of a continuous family actually, right? So you can kind of see that if you allow ideal angle and so and hyper ideal angle. So so then we have this well-known generalized triangle law. So for the hexagon, if you know alpha, beta, gamma, then the angle C is length of C is determined by this thing. And then so if you want to know B, then you have to permute these. Okay, so then you have to use B for B, you have to use what's remaining like gamma and alpha, gamma alpha, and then so on. Okay, so you have to commute this, and then this will be beta instead here. Okay, so you just have to switch the labels in some way. So that's for the hexagon. So if you know alpha, beta, gamma lengths, then the ABC is determined by this formula. Okay, so course is always positive, so there's a one-to-one relation here. So and then and then for next one, this is for quadrilateral here, and then this one is again the same, right? So only thing now is this gamma is now the real angle now here. So instead of cos, you get a cosine. Okay. Yeah. So these are all sort of you can consider these continuous. So in the complex, so you can even have a complex picture where these are or complex numbers, and you can even see this better. Okay, so cosine, cos is changed to cosine here. And then for the so once you know this, then again so if you know alpha, beta, gamma, then you determine C. So again, the other angles, other lengths A, B are also determined by these three numbers by some different formula. And then for the next one, quadrilateral, you have so if you want to know angle A, length of A, then sine H is going to be determined by these three numbers. Again, the cosine is real, so alpha, beta real, so you have to use cosine here. And right, and then finally Finally, this is trying the familiar law, right? So you have this law which everything is sine now. Okay, so um, uh, okay. Sorry, I think this h should be here. Is this reversed? Sorry, it should be reversed. So anyway, so once you have these laws, then the alpha, beta, gamma can be any positive number here. Then this makes sense. Okay, and then so for B, alpha, beta can be any positive number, but gamma has to be in 0 and pi in the middle here. And for C, alpha, beta can be any positive real number, but the alpha plus beta is less than pi, and gamma is any real number. So for C, if you see that so if you want to make a convex quadrilateral with this right angle, then this sum is less than pi. Again, that follows from the Gauss-Bonnet. You can use the Gauss-Bonnet theorem too, because the integral of inside is just the minus, because it's -1, constant curvature -1. So this is -1. So you have to look at the Gauss curvature. I mean the angle turning here, then you get this. And then for C, it can be any number, but it has to be less than pi. So that's for the hyperbolic triangle law, that the sum of the angles has to be less than pi here. Right. So that's the three laws of the. So to prove theorem A, so this is about for the T1, D2, D3, T4. So these are hexagon, and then these disk type orbifolds. So so it's just going to be that in the case of T1, you label A, B, C to be the uh, the the silvered ones, and then alpha beta to be the boundary one for orbifold. So this hexagon, you have a boundary for orbifold is like skips ones, so it alternates. So then this is a homeomorphism because this because if you know alpha, beta, gamma, which is the length of the boundary, then you know the hexagon. And if you're given a hexagon, there's of course the lengths of these boundary for orbifolds. Okay, so this is that these parameters will determine the deformation space. So therefore, this works. And then for B again. So you have this alpha, beta, gamma is not a sign now. It'll be some pi over n of some given order. So then you have alpha and beta are the free variable. Then A, B, C are determined, right? So for any alpha, beta, you get what this pentagon should be, right? Like this. So and then again here you alpha, beta are given some sub multiples of pi, and then only thing is the changeable is gamma, and then the ABC are determined. So for each boundary length, we get a unique point of the hyperbolic quadrilateral, and then here this is rigid. If you know the angle, then there's just one point. So the boundary in this case is of course empty set. So that you have to get a 1 point case. So both of these, you have to think of it as 1 point in the case. So you can think of these as cells of 0 dimension. Okay, so that's the proof for D1, D2, D3, D4. Right, so then you can do it for P1, P2, P3 because these things will double cover these orbifold. Okay, so where the fixed points are like a three union of three arcs. Okay, so if you look at the old pictures here, so this one double covers by some sort of involution about here, and then this one involution about here, and then involution about here, and then this one is actually involution about the horizontal plane. Okay, so then so if you think of this as symmetry, big symmetry. So it's double cover. So everything is actually so this involution will be realized as isometry because uh, you can use Kirchhoff's theorem to do that, and or you can explicitly show that they're actually so that you can if you use a shortest geodesics, then for pair of pans this will be because the lengths are the same, you can see that they're isometric. And then for T2 you can also do the similar things, so you can see that there is actually isometry between these involutions are actually isometries. And so it's always determined by these one of the hexagon and one of the pentagon, one of the hexagon, one of the quadrilateral and the triangle. So in that sense, these will be the so these boundary lengths are going to be just divided by 1/2 in the case of P1 and in any cases. So then the same theorem will work for that. Okay, so that's just that theorem. And then for A1, A2, A3, A4, so again there's the double cover here. Uh, so let's show how that works. Okay. So here actually the double cover will be some involution about here. Okay, so there will be, and then the involution will be something that goes around starting from here to here, ending at here. And then the another one is involution about here, and then the involution about here. Okay, so of course then the order has to be the same here, and here the order has to be the same. So anyway, so you do get a double cover by this, and then then again that's isometry. You can think of this as a isometry. So these are realized isometry, and then again the boundary is just so again the same kind of argument will show you that this is realized as isometry, and so the boundary length will determine the structure completely and so on. Okay, so if you look at the all right, so for example, this boundary length and then this boundary length, so so you have to have same length here, but then anyway, so this and this will determine this structure. So this and this will determine the structure because then it will be uniquely covered by some hyperbolic structure here. And then of course the length here, so only thing will be this length and this length will be the same. So this will determine everything. And then, so this one has only one boundary component, so it will determine everything here. So, and then of course these are zero dimensional, both of them. So this will work in that case as well. So, uh, right. So now we want to prove the Solution theorem. Then so I keep saying being in RP2, but that's sort of habit. But so the deformation space of hyperbolic RP2 structure T2 sigma is diffeomorphic to a cell of this dimension, where K is the number of cones and L is the number of corner reflectors and so on. So I will prove this fact, and then number two is that there's a principal vibration from T sigma to the T boundary sigma. So boundary sigma is the T boundary sigma is the product of the length spaces. Okay, so where the cell is the fiber is cell of this dimension. Okay. Or I should say this is a fiber by cell, not action. Okay. Uh, So sigma is a two orbifold whose components are orbifolds of negative Euler characteristic and is split into orbifolds sigma prime in P. So what we do is we have any two orbifold, then we cut it and get a sigma prime. So suppose this holds for sigma prime, okay, one and two, and then we show that it holds for sigma. So then because this for elementary only for this horse, so you prove this by induction, right? So we just have to go through each construction to prove this. Okay, so for A11, so this is just you have two cross curve you gluing in the boundary component of sigma prime, and then you glue. So we know that splitting map in this case it's just go to diagonal in T sigma prime where it's the subset where the lengths are the equal. Okay, so this is we showed that that was a vibration. So this means that the dimension here will be dropping by one, and then this is just R vibration. So the lost dimension will be gained back here. Okay, so if you look at the formula there, then there's no more singularity coming in, and then uh, and so on. So nothing really changes in the formula, and then you see that one can be proven like that. And for two, so you look at the boundary mapping vibration. Uh, so if it holds for sigma prime, then so you have to restrict it to the delta in there, and then again you see that that's vibration fairly easily. Okay, so that's how you do this here. And then for the sigma double prime obtained by cross capping, then so in that case, just a unique way to glue. So there's just this is just diffeomorphism. And of course, the Euler characteristic of the underlying space doesn't change here, and then doesn't change here, and then nothing really changes. No more singularity, and so on. So the formula, dimension formula holds, and then again these boundary thing you can also show is. So it's just getting a less number of boundary components, so it will still be a vibration. Right? Okay, so that's all you're doing. Okay. And then for A1 to 1, then so it's just doing the silvering for the boundary component. Then this is just the diffeomorphism, and just that you now have a less number of boundary components, right? And of course, it's just forgetting some component is still is going to still be a vibration. So that's all it is. And then now for the folding, so you have two order two map which fixes 2 points in one boundary component, and you glue. Then of course this will be just because there was a choice of how you rotate these uh, fixed points. So it is actually a principal R vibration. So its dimension gets bigger by one. Okay. And the point is there's two more cone points occurring. Okay, so two more cone points will arise, and the Euler characteristic will decrease by one because you got rid of the boundary component. So in general, it will just be increased by one also. This dimension formula. So it increased by one and increased by one. The formula increased by one also, and then this increased by one. So dimension, so it matches. And then of course for the boundary map, you just forgetting one boundary component, so that means you still get a vibration. Okay. So it's the same space except for it's bigger now with our vibration. So therefore, it's still going to be a vibration. Okay. And for B1, B2, B1, this is when you have a two boundary for orbifold and you glue that. So it will be a splitting map. You go to delta, which is where the invariants are the same, so the lengths are the same. So it'll be dimension will be decreased by one, and And the point is that the boundary component decreases by one because you identify them. Okay, so then this formula still works. Okay, and then of course the vibration thing also works. I mean the Euler characteristic doesn't change. Euler characteristic also change, right? Because you identify these segments. So by one, and then of course right, and then the boundary for orbifold number also change. Okay, and then so you have to work out to show that that's get the right formula. And then finally, so this one doesn't seem to appear, right? Some tech problem. Okay, but the so now if you fold the boundary component for orbifold, then so this is just going to be diffeomorphism because you did nothing to the uh, uh, you can always do it with these kind of thing. So and then whenever you have this, you can split together for boundary or before. So you, but now the order two singularity appears. One order two singularity appears, but the boundary for orbifold decreases. Okay, and then the Euler characteristic doesn't change. Okay, so then it'll work out to be the formula still works. Okay, so right. So those are the way to prove this this Thurston theorem, and